in this presentation, I'll discuss our paper titled Blind Motion Deep Learning through SinGAN Architecture. We'll first discuss deep feature learning techniques from single image, both with and without generative adversarial networks. Then we'll describe blind motion deep learning through SinGAN architecture. The common formulation of a non-uniform blur kernel is IB equal to K of M times IS plus N, where IB is a blurred image, K of M is an unknown blur kernel, IS is the sharp latent image, star denotes the convolution, and N is an additive noise. Non-blind deep learning is dependent on the assumption that the blur kernels K of M are known. However, for blind deep learning, given the blur function, we need to estimate the latent sharp image IS and the blur kernel K of M. Now, what is blind motion deep learning? The reconstruction of a sharp frame from a blurry observation is a highly ill-posed problem, which is denoted as blind or non-blind, depending on whether we have information of the camera shake or not. Videos captured by handheld devices usually contain motion blur artifacts caused by a combination of camera shake and dynamic scene content. Now, Deblurring is a training data-based generative adversarial network, and it consists of generator G and discriminator D, and it is based on the fine-tuning paradigm. Now, why do we need a training data independent method? Current solutions to the problem are data hungry and require a lot of training data to generate satisfactory results. Existing approaches like Deblurring deep generative filter for motion deep learning consist of models which take a lot of time for training. The aim is to reduce the runtime and computational power while achieving state-of-the-art results. The deep feature learning techniques from the single image basically consist of a network structure which itself acts as an implicit prior for various image restoration tasks such as image super resolution, image inpainting, etc. The initial works for deep feature learning for a single image without GAN are as follows. First is a deep image prior, where the main idea is that the network structure itself acts as an implicit regularizer. In double dip, we have an unsupervised image decomposition which occurs through coupled deep image priors. Next, we have MEDS, which is a multi-level encoder-decoder architecture for image restoration. Finally, we have deep red, which is deep image prior, powered by regularization through denoising. Now, we have internal learning techniques which are based on GAN and are trained on a single image, which include InGAN and SinGAN. As shown in the figure, InGAN is a conditional generative model and is learned from a single image, while SinGAN is an unconditional generative model and is learned from a single image. Now I'll describe blind motion deep learning through SinGAN architecture. So why do we need SinGAN for deep learning? SinGAN has proved to be very robust to deal with general natural images containing structures and textures which are complex. SinGAN produces images that are semantically similar to the training image, and it has produced good quality results for image super resolution. Thus, we have taken a step further to explore SinGAN for image deep learning. The architecture details include the hierarchical network, which consists of n GANs, and training is done in a coarse-to-the-fine fashion. As shown in the figure, Gn is responsible for capturing coarse features of the image, while G0 captures the fine features of the image. For testing, we deploy the following model. So we iteratively upsample the deblurred image 8 times and pass it through the finest scale generators G0. This is illustrated in the diagram below. The loss function is the adversarial loss function, which is the Deblurring GP loss, and the reconstruction loss, which is described below. The final training loss is the combination of these two losses and is based on the minimax objective function. So the sharp ground truth image is trained up to 8 scales, starting from the coarsest one to the finest one. While inferencing, we use the weights obtained after training and upsample iteratively while feeding the finest level generator. Some of the sample results on the GoPro dataset are as follows. In this, we train the image on the left one, and the input image which is given to the model is the one given in the middle. And as we can see, the output generated on the right has deblurred the input image to a very great extent. Here, the image of the car is deblurred to far greater extent as shown in the figure. Now here too, the face of the person is deblurred to a considerable extent. To quantify the results, we used SSIM and PSNR. SSIM on a sample of 100 images randomly picked from the GoPro dataset was 0.52, while PSNR for those 100 random images was 15.3. Here are the primary references. We show how to perform training data independent blind motion deep learning using SinGAN. The training data independent solution to the blind motion deep learning problem could generalize well by learning features from a single image. Thank you.